Good morning, dear students. I am here again for my course Aircraft Systems. I am in the last module of this course, which is Airplane Control System. Today I am going to talk about Flight Control System, primary and secondary flight control. As you know that I am Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. As of now, I have covered 4 modules. In module 1, I have given the description of different types of aircraft systems. In module 2, I have discussed about electrical system, power distribution system, and so on. In module 3, I have discussed about hydraulic system and pneumatic system. In module 4, I have discussed about engine control and its systems. Now I am in the airplane flight control system. Here I am going to discuss about flight control and its importance. In this, we have the syllabus of airplane control system. We have flight control system, primary and secondary flight control, conventional system, power assisted and fully powered flight control system, power actuated system, engine control system, push-pull rod system, flexible push-pull rod system, control linkages, actuation types, description and redundancy, component, modern control system, digital fly-by-wire system, control, more laws, implementation, autopilot system, and so on. In today's lecture, I am going to discuss about flight control system. In this, I will be discussing about introduction, development of control system, the fly-by-wire, principles of flight control system, flight control surfaces of a combat airplane, role and yaw control of military airplane, secondary flight control system. So these topics I am going to discuss in today's class. Flight control system, if we talk about the flight control, this you can see the olden type of aircraft in which you have a lot of wires. These wires are visible here. These are the wires. These wires and how these things are connected with the elevators and ailerons. So it is shown here like that. It is some of the defense aircraft. That time Moran saw near. So earliest biplane flight control was achieved by warping wings and control surfaces by means of wires attached to the flying controls in the cockpit. So this you can see here that in the earlier days these wires were attached to the flight control. For the primary flight control, that is elevator, aileron and the rudders, and they were warped in some wheel, and from where pilot used to make like this. Okay. Exercising control was clearly rudimentary and was usually barely adequate for the task in hand. But that time this control was very difficult and it was very impossible task. Very slow work we can do in that. The articulated flight control surfaces followed soon after, but the use of wires and pulleys to connect the flight control surfaces to the pilot control. So the pulleys and the wires were used to change the direction. Like this is the pulley and the wire will come from this side. It is a wire and this is the pulley and it will move. So this pulley move either this or in this, any direction like this. So if the wire is moving, your pulley will also move in this or in this. Accordingly, it will your control will be deflected and the direction of the flight you can achieve. The higher speed resulted in a higher load on the flight control surfaces, which made the aircraft very difficult to fly physically. Hydraulically powered actuator boosting the efforts of the pilot to reduce the physical effort required. This brought another problem, that of feel. By divorcing the pilot from the true effort required to fly the aircraft, it becomes possible to undertake maneuver which could overstress the aircraft. So, as and when the aircraft speed is increased, a more load is experienced in the wing and also in the flight control. It was very difficult to handle by the human pilot. So now, after that, they started the powered system. In that, hydraulic fluid was used, and it is hydraulically actuated boosters. So pilot will give a little effort and it will be acted upon. This brought another problem, that of feel. So in that, pilot was not able to feel that how much he is turning. Like if you are driving your car or your bike, you can understand what is the speed, because if you don't see the meter also, you can understand by your experience. But if it is hydraulically operated, pilot we are not able to understand that how much he is putting the effort on the control. So a feel problem was existing. So by diversing the pilot from the true effort required to fly the aircraft, it became possible to undertake maneuver which could overstress the aircraft. It was necessary to provide an artificial feel so that the pilot was given feedback. So it is very much essential that how much pilot is putting the stick, nose down, nose up, rolling left, rolling right. Pilot has to feel in his hand that how much he is turning, how much it is nose up, or it is a rudder. He has to feel in his leg that how much effort he is putting and how much action is taken by the aircraft. So we need some artificial feel, that pilot should experience that how much the feel it is felt. The need to provide artificial means of trimming the aircraft was required, as mag trim devices were developed. So the mag trim devices for the high speed aircraft was developed. High performance aircraft to experience roll, yaw coupled oscillation, commonly called Dutch roll. So in high speed aircraft, the roll and yaw coupled oscillation means rolling and the yawing. This is called Dutch roll, like this. Dutch roll. So high performance aircraft to experience roll, yaw coupled oscillation, commonly called the Dutch roll, led to the introduction of yaw damper and other auto stabilizing system. For a transport aircraft, these were required for passenger comfort, whereas on military aircraft, it became necessary for target tracking and weapon aiming reasons. So for the transport aircraft, these were required for the passenger comfort. Otherwise, it will go like this. No, passenger will like to sit. So we need something to compensate or to absorb this oscillation, which are in the form of Dutch roll. And military aircraft is necessary for target tracking and the weapon aiming regions. The implementation of yaw damper and the auto stabilization system introduced electronics into the flight control. So this yaw damper is used so that it should not go very much, Dutch rolls should not be there, and auto stabilizing system introduced electronics into the flight control. So slowly, previously it was only wire, after that pulley wire, then hydraulic system came. After hydraulic system, the electronic system was introduced. So autopilot had used both electrical and air-driven means to provide an automatic capability of flying the aircraft, thereby reducing crew workload. So autopilots were introduced. In that, pilot will feel very comfortable. This is done by the electrically as well as mechanically air-driven means. The sensors are used to provide this type of system. Automatic capability of the flight of the aircraft is achieved. The workload of the pilot and the aircrew also is tremendously reduced. The electronics used to perform the control function comprised analog sensor and actuator devices which became capable of undertaking high integrity control tasks to guard against equipment failure. So now the electronics used to perform the control functions comprised analog sensors and actuator devices, which became capable of undertaking high integrity control tasks to guard against equipment failure. Now, development of the control system. Removal of mechanical linkage between the pilot and the flight control actuator and rely totally on electrical and electronic means to control the aircraft. The control and stability augmentation system, that is CSAS, the control and stability augmentation system fitted to the aircraft retained some mechanical reversion capability in the event of total system failure. It is called hybrid, means it is automatic control and the mechanical control. In case autopilot is failed, then pilot can take over, and it is called the hybrid system. The rapid development and maturity of digital electronic led to digital fly-by-wire system. The rapid development and maturity of digital, slowly this computer has come up and the digital systems have come up. So the fly-by-wire system, it is electrically operated control. Fly-by-wire means fly by the wires, not by the pulleys and this thing. Primary flight control actuators, which have to be able to accommodate multiple channels inputs and also possess the necessary failure logic to detect the isolate failure. So it should be also able to detect the isolate failure of the aircraft. Now I will discuss about the principles of flight control. In this you can see that we have the aircraft here. This aircraft, it is called the roll axis, which is in the x direction. This is the pitch axis and this is the yaw axis. So we have the three axes. Roll axis means the aircraft will roll with respect to this axis. Okay. Aircraft will roll with respect to this axis, and pitch will be in this. So it is a positive pitch. This you can. So this pitching will be done by this pitch axis, means nose up and nose down with respect to this pitch axis. Rolling of the wing going down or up will be from the rolling axis, and nose going towards the left and the right will be done by the yaw axis. And here, if nose going up is positive, right wing going up is positive, and nose going towards the right is also positive. So it is definition of the flight control axis. The motion of an aircraft is defined in relation to translational motion and the rotational motion around a fixed set of axes. It is shown in this diagram. Translation motion is that by which a vehicle travels from one point to another in a space. Rotational motion relates to the motion of the aircraft around three defined axes: pitch, roll, and yaw. Nose up and down with respect to pitch axis OY, called the pitching. So if you see here, O and the Y is here, so it is called the pitching. Nose side by side with respect to this axis, it is called the yawing axis. Yawing. Wing up or down with respect to the roll axis OX. This is the O and this is the X. This is the Y and this is the Z. Okay. So it is called the wing up or down with respect to roll axis OX is called the rolling. Climb only in pitch axis OY. Climb will be with respect to the pitch axis. Turn is around the roll axis and the yaw axis. And if it is turning, it will be in around X axis and OX and the OY axis. Climbing or descending turning maneuver involves all the three axes. Flight control surfaces of a combat airplane. So here, primary flight control in pitch, roll, and yaw is provided by the control surfaces described below. Pitch control. Canard provides the very powerful pitch control authority required by an agile high-performance aircraft. The position of the canard in relation to the wings rendered the aircraft unstable. Without the benefit of an active computer-driven control system, the aircraft would be uncontrollable and would crash in a matter of seconds. So here if you see, the position of the canard in relation to the wing render the aircraft unstable. So this canard is making aircraft unstable without the benefit of an active computer. So we need a active computer, then only it will work. Driven control system, the aircraft would be uncontrollable and would crash in a matter of seconds. It may appear to be fairly drastic implementation. The benefit in terms of improved maneuverability enjoyed by the pilot outweigh the engineering required to provide the computer control or active flight control system. So we have to see that which control is suitable. This you can see here that these are the 4 planes for pitch control and stabilization and performance optimization. Intake scheduled for performance. Air data. Here is the gyro. Acceleration plus coupling. Here we have the rudder and the yaw trim control here. And here we have the inboard and outboard flaperon for the pitch control. So it is delta wing fighter aircraft. The configurations are like that. Roll control of military aircraft. So roll control is provided by the differential motion of the foreplane, augmented to a degree by the flaperon. In order to roll to the right, the left foreplane leading edge is raised relative to the airflow generated, greater lift than before. Right foreplane moves downward by a corresponding amount of relative to airflow, thereby reducing the lift generated. The resulting differential forces cause the aircraft to roll rapidly to the right. To some extent, roll control is also provided by differential action of the wing trailing edge flaperon. However, most of the roll control is provided by the foreplane. Yaw control of military airplane. Yaw control is provided by the single rudder section. For high performance aircraft, yaw control is generally less important than for conventional aircraft due to the high level of excess power. There are nevertheless certain parts of the flight envelope where control of yaw or side slip is vital to prevent roll yaw divergence. So here few very sophisticated fighter aircrafts, there the rudder, this you can see here, this is your vertical tail and the rudders are here. F-22 here, the rudder, if you see it is which type of rudder, it is in this angle. And F-117 the rudder, it is like a V shape. Okay, so like this, different types of controls are used for different purposes. So yaw control for military aircraft is very difficult task, because in military aircraft we don't want that its radar signature is increased. We try to make it stealthy aircraft, and this you can see the shape of these aircrafts are very stealthy. Your radar may not be able to capture such type of configuration. So like this aircrafts are made. Secondary flight control, the high lift control is provided by a combination of flaperon and the leading edge slats. The flaperon may be lowered during the landing approach to increase the wing camber and improve the aerodynamic characteristics of the wing. The leading edge slats are extended during combat to increase the wing camber and the lift. The penalty for using these high lift devices is increased drag, but the high level of thrust generated by a fighter aircraft usually minimizes this drawback. They extend air brake to 30 degrees, thereby quickly increasing the aircraft drag. The air brakes are deployed when the pilot needs to reduce speedy quickly in the air. Air brake extended during the landing run to enhance the aerodynamic brake effect and reduce wheel brake wear. Here we can see the secondary flight control system. Here we have the slats. Slats are ahead of the leading edge. This is your slat. This one is a slat, and these are the flaps are behind. It is called the trailing edge. The flaps are in the trailing edge, and the spoilers are at the center. We are putting the spoiler, and here we have these trim tabs. So these are the few secondary flight control systems which are used here, and how these things are operated. Secondary flight control. This you can see here. It is a flaps, and here is a tab, a trim tab here, a servo tab is here, balance tab is also here. It is the control horn is here. It will come out, so it will balance. Control horn, and this is the spring cartridge. So like this, different types of tabs are shown, and these tabs are also called the secondary flight control systems. So this, whenever we want for a high lift, we have to put down, especially in maneuvering and all. And if you want during landing and this takeoff, we use the flaps. During landing, we use high flaps. It may go up to plus 20 degree. During for landing, 20 to 25 degree. For takeoff, 10 to 15 degree we use. So this is the your angle of deflection of the flap. This we use normally in the system. Now, if you see the rudder and aileron trim tab system, trim doesn't only apply to the elevator, as there is also trim for the rudder and aileron. The use of this is to counter the effect of slipstream, or to counter the effect of the center of gravity being is one side. This can be caused by a larger weight on one side of the aircraft compared to the other, such as when one fuel tank has a lot more fuel in it than the other, or when there are heavier people on the one side of the aircraft than the other. So this rudder and aileron trim tabs are used also to balance the center of gravity of the aircraft. These things are also used. Now, secondary flight control, the types of flap systems. First one, we have the Kruger flap, hinge flap on the leading edge. So these are the in the leading edge. Plain flaps rotates on the simple hinge. Split flaps, upper and lower surface are separate. The lower surface operates like a plain flap, but the upper surface stays immovable or moves only slightly. Fowler flaps slides backward before hinging downwards, thereby increasing both camber and the chord, creating a larger wing surface better tuned for lower speeds. So this Fowler flaps, in their your chord will also increase, and angle of attack will also increase. Slotted flap, a slot or gap between the flap and the wing enable high pressure air from below the wing to re-energize the boundary layer over the flap. This helps the airflow to stay attached to the flap, delay the stall. Blown flaps, system that blow engine air over the upper surface of the flap at certain angle to improve lift characteristics. Flap control system, flaps are hinge surface on the trailing edge of the wing of a fixed wing aircraft. As flaps are extended, the stalling speed of the aircraft is reduced. Flaps are also used on the leading edge of the wing of some high-speed jet aircraft, where they may be called the Kruger flap. Flaps increase the camber of the wing airfoil, thus raising the lift coefficient. This increase in lift coefficient allows the aircraft to generate a given amount of lift with a slower speed. Therefore, extending the flap will reduce the stalling speed of an aircraft. They also increase drag with help of to slow the aircraft. Here you can see some flaps. It is a plain flap. It is coming down like this or up as I went to call. It is split. It is same, only this one part is coming down here. Okay, so here it is called the Fowler. It will extend from here to here, and this is called the slotted. Some gap is created. In this, no gap. No gap. In this, no gap. In this also no gap. But in this slotted, it will create the slot, and this will give some high kinetic energy of the wind, and the separation of this can be avoided. Okay, so here we have the different, it is, this you can see, it is a nose type of slot, triple slot flap here, and these are also the flaps. So these are the flaps are shown here. Okay, how these things are working, this you can see the mechanism, and this is the triple slot. So here one slots, two slots, and the three slots are generated. These slots are used for generating additional lift by putting some extra kinetic energy. Next is very important, is a spoiler. This you can see, these are the spoilers. Some part is extended as and when required. These are the spoilers. Okay. So on low drag aircraft like sailplanes, spoilers are used to disrupt airflow over the wing and greatly increase the amount of drag. So the purpose of spoiler is to increase the drag. This allows a glider pilot to lose altitude without gaining excess air speed. Spoilers are sometimes called the lift dampers. Dumpers, not damper, it is dump, means putting down. Spoilers that can be used asymmetrically are called the spoileron and are able to affect the aircraft roll. And they are able to affect the aircraft roll. Rolling effect by the spoiler, how these spoilers are affecting. If you see here, the left wing, if you make up like this, here the lift will be reduced. This wing will have the reduced. This will have the reduced lift, and this will have the increased lift. Increased lift. Okay, so in this way, we can find that this aircraft will start rolling like this. So if you want to roll also, you can increase or decrease this spoilers. High lift devices. Next is the slat. So these are the slat. It is like a leading edge flap. Something will come out from the wing. These are your winglets. Okay, so slats, also known as the leading edge devices, are extension to the front of a wing. Just you can see here, this is the wing, and in the front we have the slats, and are intended to reduce the stalling speed by altering the airflow over the wing. Slats may be fixed or retractable. Fixed slats give excellent slow speed and STOL capabilities, but compromise higher speed performance. Retractable slats, as seen on most airliner, provide reduced stalling speed or takeoff and landing, but are retracted for cruising. Leading edge extension. Leading edge extension, or LEX, also referred to as leading edge root extension, or LERX, or strake or the chines, are fillets added to the front of the modern fighter aircraft wing in order to provide usable airflow at high angle of attack. They are typically roughly triangular in shape, running from the leading edge of the wing root to the point near the cockpit along the fuselage. They tend to be fairly small in span, extending out less than a meter. In effect, they are a small delta wing grafted onto the front of the normal wing. So this you can see here, leading edge extension. Just you can see here, this is the leading edge extension. Something is coming out like this. So They are the leading edge extension or root extension or LERX or strake or chines or fillets added to the front of the modern fighter aircraft wing in order to produce usable airflow at high angle of attack. They are typically roughly triangular in shape. Okay, so just you can see it is like a triangle here. It is provided here. Okay, so leading edge cuff. Next is the leading edge cuff. This you can see the yellow color. This is the leading edge cuff. So this leading edge cuffs are a fixed aerodynamic device employed on a fixed wing aircraft to modify the airfoil used. They may be either factory installed or more commonly an aftermarket modification. In most cases, a leading edge cuff will droop the leading edge of the airfoil. This has the effect of causing the airflow to attach better to the upper surface of the wing at higher angle of attack, thus lowering the stall speed. This allows lower approach speed and shorter landing distance. So it is used to lower approach speed and the shorter landing distance. Wing vortex generator, it is called VG, vortex generators. The wing vortex generators, in order to reduce the drag caused by supersonic flow over portion of the wing, a small airfoil called the vortex generators are installed perpendicular to the surface of the wing. They are mounted in complementary pairs. This causes the vortices being developed to aid one another, thus increasing the effect. On some aircraft, fences are installed on the wing and ailerons. This gives more stability and control of the aircraft, reduces buffeting and reduces high speed stall characteristics. Depiction of the wing. This is a vortex generator. This you can see here, it is like this, and some distance it is fixed, and they are the like this. Okay, it is airflow will go like this. This you can see here, it is shown in this diagram like this, a very small part. This you can see here. Flow will go from here and flow will go from here like this. So this vortex will be generated, and this will be very useful for the high speed aircraft, and the drag will be reduced tremendously by using such type of configuration. Now wing fence, winglet and the tip vortex. So this you can see here, the wing fence means the flow from this side it will stop. So the span wise flow is restricted. Winglets are also here. They are used to reduce the drag. If you see here, if you have this winglet here and here you don't have, this much wingtip vortices will be generated. But if you have here blended winglet, only up to here and very small this wingtip vortices are formed. So this is the advantage of the winglet. So here we have one small diagram which shows the different special type of aircraft, and in this you can see how the vortices are formed. These are the references which I am taking, that Moir I and the Seabridge A aircraft systems, mechanical, electrical and avionics subsystem. Moir I and the Seabridge A, design and development of aircraft systems and introduction. Thank you very much. If any questions are there, you are welcome to ask. Otherwise, I am ending here. If any questions or query, you can send me to yddwivedhi@gmail.com. This is my email address. You are welcome to send any query if you want. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.